Hello everyone. Welcome to the second lesson in your journey of learning calculus. This course is designed to guide you step by step through the fundamental concepts of calculus, building your knowledge from the ground up. Throughout this course, we will explore everything from the very basics like understanding functions, limits and derivatives to more advanced topics like integrals, infinite series and differential equations. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the second lesson in learning calculus. Well, as we continue learning from the first lesson, we started with understanding what is a function. Now here is something very interesting which is called a piecewise defined function, and what is that we are going to explore now. Now sometimes a function is described in terms of pieces, small pieces, by using different formulas on different parts. Now here is a definition of what is a piecewise defined function, which is defined in different pieces depending on the input value. These functions are typically expressed using certain conditions which express on the certain amount of input range. Now typically this is how a piecewise defined function looks like. It is defined for different pieces. Here you can see f of 1x if x is in a certain range, then f of 2x if x is in another range, dot 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 dot, and it goes up to f of n which if x is in some other range, for example n range or whatever. So from here what we come to know is that this function, if I take it, then it has got two formula. The first one is this one, which is called x is greater than equal to 0, and the second one is this one, which is x less than 0. So from here what we come to know, the function f of x, this is different expression to x within its specified range. So if it's given a specified range where if 1 of x is a different expression for x within its specified range. Now from here what we get is this kind of a graph. Now if you look closely into this graph, you will see the right hand side of the equation means that the function equals x if x is greater than 0. So this is also known as absolute value function. We will come to that. And piecewise defined functions often arise when we need to plot certain real world model data. So here you can see that the term absolute indicates that it represents a number size in an unbiased way, irrespective of its direction, whether it is going in the positive or in the negative. So here, as you can see, this one which has highlighted in blue, this is basically what we call is the absolute function, the first formula or the second formula. So the absolute value function is named because it measures the absolute or magnitude of a number and it ignores its sign. So the absolute value of a number represents the distance from 0 on the number line regardless of the direction. So as you can see that whether it is plus 5 or it is minus 5, it gives an absolute value that is within the modulus of 5. So this is something which is called the piecewise defined function. If you plot it, the graph will look something like this. Now you might be wondering that we understand that a piecewise defined function is useful for different pieces given conditions, and it specifies a range, and this range can take two formula, and it is also called absolute value function. But the question is that what is the reason? I mean to say there should be a practical reason for using piecewise defined functions. Until we know the reason, then all the functions and the formula are just stored in our books and in our copies. It doesn't make any use. So let us find out what are the some of the reasons for using piecewise defined function. As I have told you earlier that it is used for modeling real world situation with changing conditions. Now for example, tax rates. Now tax rates in tax calculations, income is often taxed at different rates because your income, my income, another person's income are not the same. So if you are given a certain bracket, so you need to calculate tax rates where it is used. Second one is shipping costs, because shipping costs vary based on what? Based on weight, region or shipping speed. A piecewise function can represent these changing accurately. As you online order something online, so some parcels cost more, some parcels cost less, some parcels are delivered, it is what is called Amazon Prime, so likewise. Also you will see it helps in handling discontinuous behavior, because some functions have a discontinuous or jumps. discontinuities where the function abruptly changes its value, as you have seen that the graph falls down abruptly. So piecewise defined function can accommodate these jumps and represent functions that are not smooth or continuous. It can also help to simplify complex equations, because in mathematics and engineering certain functions are easier to define and work with when broken down into small manageable pieces. For example, waveforms in electrical engineering such as square waves or sawtooth waves are easier to describe piecewise. Also, you will see that piecewise defined functions helps us to define customs behavior in specific ranges. So we want to restrict a function to a specific range, creating a different outcome, we use that. You will also see that piecewise functions are helpful when patterns don't follow a uniform rule across a certain range of values. For example, population growth may follow different rates over time, and these would require different expressions for different time of intervals. So taking all those tax rates, shipping costs, etc., what we can say is that piecewise defined functions are useful because they allow us to describe relationships or processes that changes depending on the input, and this change can be on different conditions, intervals, depending upon the different contexts. So as you can see that industry, our daily life is heavily dependent on piecewise defined function. Now all these things won't be very useful until and unless I give you certain examples. So here are certain examples of what are called piecewise defined function. Now the first example is what is called a step function, and it looks something like this. So here you can see the function returns different constant values based on whether x is negative, 0 or positive. So this is what is called a step function. The second one is called the tax rate function. We are just talking about tax rate, that your income, my income, and the person's income are different. So tax rate function, as you can see, looks like this. As you can see in this example, that the tax rate in income in X lies within certain thresholds. So from here what you can see that 0.1x, if 0 is less than 50,000, then 1 lakh, and so on. So piecewise defined functions overall you can say are useful when modeling situations where a certain set of rule or relationship changes based on different conditions or intervals. Let me give you some more examples to make things clear. As you can see, this is another example of piecewise function. This is the first, second, and the third formula. This is defined on the entire real line, but has got values for different formulas. So for example, depending on the position, now if I say for example, as you see that it is defined on the entire real line. Now say for example, if I take the value of f are given y equals to minus x, when x is less than 0, when y equals to x squared, when 0 is less than equal to x and less than equal to y, when x is greater than 0, y is equal to 1, then the value is x greater than 1. So for y equal to minus x, when x is less than 0, y equal to x squared, when 0 is less than equal to x, less than equal to y, and when y equals to 1, then when x is greater than 1. So the function, this one is just one function whose domain is on the entire real set. However, the graph looks something like this. So here now you can see that y equals to minus x is on this direction, all coming from the same left hand side equation. Then y equals to 1 comes in here, and y equal to x squared comes in here. So these are, examples of piecewise defined function, because as before learning calculus, understanding functions is very important at the grassroots level. Now there can be another example, the function whose value at any number of x is the I would say greater integer, less than equal to x is called what is called a greatest integer, or the integer floor function. So it is denoted by this this one, and it looks something like this. Right, so this is something what it looks like. Now if I now plot, so from this range 2.4 equals to 2, these are all ranges. So if I now plot the graph, you can see that if you take 2.4 equals to 2, it comes somewhere around to here, then again here, and then again here. If you take the minus signs also, you can see that minus 2 equals to minus 2. In this way things are being plotted. So this is basically called the greatest integer function, or the integer floor function. How it happens? It happens when x is the greatest integer less than or equal to x, then it is called the greatest integer function. Okay, so going further, you will see that there is something where the value is called least integer function. From greatest we come up to least. So here is the definition: the function whose value at any number x is the smallest integer greater than or equal to x. It is called the least integer function or integer ceiling function. Ceiling means you make up a certain ceiling, you give a certain bracket, restrict something. So that is why it is called integer ceiling function. This is denoted within square bracket, which is called x. And if I try to show you in graph, now again you see something like this. This is how it happens. This is what is called integer ceiling or the least integer function, y equals to x, y equals to s, and how it is being plotted. Now, if I give you a numerical example, for example, this one, the cost of parking x hours, whatever be the number of hours in a parking lot that charges $1 for each hour or part of an hour. This is how we can give an example. Further, as you can see, if I take, for example, x is the smallest integer such that n is less than equal to, greater than equal to x, then 3.2 equals to 4. Since 4 is the smallest integer greater than 3.2, I take this one. Since -1 is the smallest integer greater than -1.8, I take this one, and these are for all integers x equal to x. So the ceiling function, sometimes remember, it becomes very, very useful where we need to round up to the next integer, because we want an approximate value where we set this value, so we call it as integer ceiling function. We move on to the next type of functions, which are called increasing and decreasing functions. What are those? We will look into the next part of the video. Now, the very simple example of increasing and decreasing function definition is this: if the graph of a function climbs or rises as you move from left to right, so you're moving from left to right, we said the function is increasing. If the graph falls or descends as you move from left to right, the function is decreasing. So that is how, but this is a kind of an English definition. However, the mathematical definition is something like this. Let us suppose that f be a function defined on an interval I, and there are 2 points x1 and x2 in I. Then this is how it looks like. If f of x2 is greater than f of x1, whenever x1 is less than x2, then it is said f is said to be increasing on I. And if f of x2 is less than f of x1, whenever x1 is less than x2, and then f is said to be decreasing on I. Now, this is important for us to realize that the definitions of increasing and decreasing function must always satisfy for every pair of points on x1 and x2 in I. Now, remember that we are using x1 is less than x2 because we use the inequality sign. We are using this one, x1 is less than x2, because we use the inequality sign less than to compare the function values. Instead, instead of this one less than equal to, it is sometimes said that f is strictly increasing or decreasing on I. So the interval I might be finite, which we call, or infinite, and by definition never consist of a single point. So let me come back again to make things clear. Now, this part you must understand. It must be important to note that the increasing and decreasing of function must be satisfied for every pair of points which is lying on x1 and x2 in I with x1 less than x2. And because we use the inequality less than to compare the function values instead of this one. So instead of this one, we are using what is called the less than equal to. This is important. Instead of the less one, we are using to compare the functions, we are using less than equal to, because it is sometimes said that f is strictly increasing or decreasing on I. So this sign is important because we are using this inequality. So this is what is called an increasing and a decreasing function. Now, if I plot on a graph how it will look like, it will look something like this. Here you can see the function is graphed is decreasing, where from minus infinity to 0 and increasing where from 0 to 1. These are the two intervals. So from here we can say that the function is neither increasing nor decreasing on the interval 1 comma infinity because of the strict inequalities used to compare the function's values in the definitions. So it is decreasing from minus infinity to 0, one interval, increasing on 0 to 1, but the function is neither increasing or decreasing on the interval 1 comma infinity. Let me give you a quick example of the increasing and decreasing function on a very simple terms. So let us consider the function f of x equal to x squared, and let us take 2 points x1 and x2 on the axis, this line where we say x1 is less than x2. So from here what we can see, the f of x2 is equals to x2 squared and f of x1 is equal to x1 squared. Now we know that x2 squared is less than x1 squared because it lies far off, is greater than x2 squared is greater than x1 squared. We can conclude that f of x2 is greater than f of x1, and this holds true for any pair of points between x2 where x1 is less than x2. Therefore we can say from here that the function of f of x equals to x squared is increasing. And it is increasing, remember, for on the entire real number line. Now let us consider the same points x1 and x2, and we consider another function g of x equals to minus x. So if we take the 2 points same x1 and x2 on the axis where x1 is less than x2, we have g of x2 equals to minus x2. I'm so sorry, this would be x2 not x1, this one x2 and this one x1. Since we know that x1 is less than x2, we can conclude that minus x2 is less than minus x1. Therefore from where we can say g of x2 is less than g of x1, and hence we can conclude that g of x equals to minus x is decreasing on the entire real number line. I'm so sorry, this one should be x2. Apologies for this. So from here what we can get is that an increasing functions means that as x increases, the corresponding y value, that is f of x, also increases in the first example. A decreasing function means that as x increases, the corresponding y value f of x also decreases in this part. Okay, we move to the next type of function which is even more interesting, which is called an even and odd functions, and we get beautiful graphs on this. So from here what we can say, the definition that the graphs of even and odd may have a characteristic symmetric properties. Okay, I will tell you what it is. A function y equal to f of x is an even function if there is a condition, if f of minus x equals to f of x, and it is an odd function if f of minus x equals to minus f of x. So just remember, the name odd and even actually comes from the powers of x. Let me give you certain examples. So y is an even power of x if, for example, y is an even power of x, as in this y equal to x squared, y equal to x4, these two. Then what we see is that it is an even function because minus x squared even give x squared, minus x4 given positive x4. And if y is an odd power, so here you can see I have circled this. That means these are even powers. So if y is an odd power of x, as in y equals to x or y equals to x cube, then what it happens, minus x1 to the minus x to the power 1 gives minus x, and minus x cube gives minus x. So here again you can see that the powers are negative. So as I was telling, that even and odd actually comes from the powers. Now if I now plot in a kind of a graph, so the graph of an even function, let us see how it looks like. This is the graph of an even function, and it is actually symmetric about y-axis. Now you might be wondering, what do I mean by symmetric? Symmetric means that if you even flip it, you get the same result. So here's the symmetry about the y-axis. So you can see it is the symmetric about y-axis. Now since f of minus x equals to f of x, a point xy lies on the graph, and if and only if the point minus x lies on the graph. So here you see both the thing lies on the same graph. Whereas if I get this kind of a graph, the graph of an odd function, this is symmetric about the origin. Why? Because f of minus x equal to minus f of x. This condition we have seen earlier. So a point xy lies on the graph if and only if the point minus xy lies on the graph. Here you can see again. So what we can say is that a graph is symmetric as I was saying, symmetric. So graph is symmetric about the origin if rotating around 180 degrees about the origin leaves the graph unchanged. And here you can see that the definition implies both x and minus x must be in the domain of f. It must be in the domain of f. So here you can see that the point x comma y lies on the graph if and only if the point minus x comma y, this one, I'm sorry. Let me go back. Yeah, minus x comma y lies on the graph. This one and this one, and if you rotate it about the origin, leaves the graph unchanged. So these are called even and odd function. Now let me give you some quick examples, then things will be much more clearer. Say for example, if I take f of x equals to x squared, then I would say this would be again equals to x squared. The value of this would be minus x squared equal to x squared. This is something I am trying to say, that how do we calculate the values. So even function f of x equal to x squared, even function minus x squared equals to x squared. This is true, and this is again for all x symmetry about the y-axis. That means if you plot it, this will be symmetry about the y-axis. Next condition, f of x equal to x squared plus 1, even function again, because minus x squared plus 1 equal to x squared plus 1, and this is again symmetry about the y-axis. This is for all x, it is symmetry about the y-axis. See this graph, this one. We will come to this why we have added x squared plus 1 later. The next one, f of x equal to x, this is an odd function. Why? Because minus x leads to minus x for all x, which is symmetry about the origin. And f of minus x equal to minus x plus 1, this is not odd. This is not odd. Why? Because minus f of x equals to minus x 1, but the two are not equal. These two are not equal. And here you can see what I was trying to tell you, that we add the constant term plus 1, this one, we add the constant term plus 1 to the function of y equals to x squared, and it is still even, and its graph is still symmetric about the y-axis when we add the constant term 1. So let me tell you again, if we add a constant term 1 to the function y equal to x squared, then what happens? The resulting function y equal to x squared is still even. Why? Because and its graph is still symmetric about the y-axis. So this is something important, that how these functions and the symmetries look like and how they behave. Another important graph which comes forward in terms of this understanding, this one, minus x plus 1 not equal to x plus 1 for all x equal to 1, looks like this. Now here you can see that even here also, even if we add the constant term 1 to the function y equals to x, there we have added where? We have added that function y equal to x squared plus 1. If you go to the previous slide, you will see that this is added to y equals to x squared plus 1, and it is still even. What we are doing right now is that we are adding y equal to x plus 1. In this, where we get x is not equals to 0, we are adding y equals to x plus 1. So when we add the constant term y equal to x plus 1 to the function y equal to x, here it comes, the resulting y equal to x plus 1 is no longer odd, since the symmetry about the origin is lost. So the function y equal to x plus 1 is also not even. So this is how we do. The next part of the video, we will try to look into something very common to all of us, which are called linear functions. What are linear functions? Coming up into the next part of the video. So linear function, as you know, is something linear which creates a kind of a straight line when graphed and can be defined by the equation form y equal to mx plus b. Somebody writes y equal to mx plus c, doesn't matter. Here what happens is that for the constants, m and b are the constants, and this one is look something. So if I now plot fx equal to mx plus d, it leads to an array of lines f of x equal to mx where b equals to 0. So these line all passes through the origin. All of this line, as you can see, they pass through the origin. So where b equals to 0. This is important. Now there are certain characteristics of a linear function. Number one is that the slope m, which you can see all these blue lines and the yellow lines, the slope m represents a constant rate of change. Meaning what? That the function increases or decreases at a steady rate, at a very steady rate as x changes. Next is that the graph of a linear function is always a straight line, and in a linear function x has an exponent of 1. Remember, it is an exponent of 1 and no higher powers or other functions. For example, square roots or logarithms, which we will see in the due course of time, x appears. And this is what I was calling that the constant rate of change. You see the lines are all constant rate of change, which measures that the increases or decreases at a steady rate. As I was talking that there are no exponents, now we come to, okay, so this is another graph which shows, this is something which shows a steady, this blue line shows a steady rate of change. So as I was talking that there are no exponents, now we come to something which is even more interesting, which are called power functions, and we will look into that into the next part of our video. So what is a power function? It's very simple. Function, if you say something like this, where xa, and here let me do this, x and x are variable, and a is basically the what is called the power or the exponent. So there are several important cases to consider. Now if I consider this one, power, as you understand that as we increase the power, the characteristic of the graph also changes. So f of x equals to x to the power n, and if you take, say for example, 1 2 3 4 5, and in this case what we are doing is that we are taking n, that is what is n, a equals to n, which is a positive integer. Now this would lead to various different types of graphs. You can see one by one it is coming, where y equals to x, then x squared, then y equal to x cube, x4. As I told you, we will go up to x to the power 5. Now what is important is that you can see how the shapes of the graphs have changed. Now if I take this one, x equals to 2 and 4, that means even powers, you will see the graphs are all U-shaped. The graphs are all U-shaped and symmetric about the y-axis. And if I take the odd powers, for example 1, 3 and 5, you will see the graphs are mostly S-shaped except the 1 power. As the power increases, the graph changes, and they are symmetric about the origin. So from here what we can say, again you see that the even powers have got a U-shaped curve and the odd powers have got an S-shaped graph. So as n increases, the curves tend to flatten out near the x-axis, and conversely the curves become more steeper where x is greater than or equal to 1. So this indicates that the function changes more rapidly as we move away from the origin. Are you getting my point? I hope it is clear. When n increases, the curves tend to flatten out near the x-axis on the interval. This means that the function values change less rapidly. But when the curves become steeper, x greater than or equal to 1, this indicates that the function values changes more rapidly as we move away from the origin. One is moving away from the origin, and one is saying that it is the function is less rapidly changing. So here, as you can see, I have given a kind of a summary that as the flattening and steepening depends on the powers, as n increases, the higher powers dominate. So each of these curves, remember, each of these curves passes through the point 1, 1, which is the origin. And the functions with even powers are symmetric about the y-axis, with odd powers are symmetric about the origin. If we take another kind of case where a equals to -1, remember what do we mean by a? We mean by a as the power of the exponent. If we take a equals to -1 or equals to -2, then the graph of the function f of x equals to x to the power -1, which can be written as 1 upon x, can be written like this. And now if I take this one, this is known as hyperbola. And here you can see when it becomes a hyperbola, as x is not equal to 0, the graph y equals to 1 upon x is an hyperbola which approaches the coordinate axis far from the origin. And this actually shows the graph of the function f is symmetric again about the origin. Now if I take the next one, for example we take g of x, which is again 1 upon x squared, it will look something like this. And here you can see the graph of the function g is symmetric around the y-axis. So earlier the function was symmetric about the origin, and here it is symmetric about the y-axis. So from here what we can say, the graph of the function f, that is the first function, which is the hyperbolic function, which is on the left hand side, is symmetric about the origin. That means if f is decreasing on the intervals, and the graph of the function g, which is on the right hand side, is symmetric about the y-axis. That means g is increasing on minus infinity to 0 and decreasing from 0 to infinity. And the domain range, remember, x is not equal to 0 and range is y is greater than 0. Now, similarly, if I take another example where a is 1 upon 2, 1 upon 3 and so on, then what we can get is that the graph of the function, for example, f of x equal to just square root of x, then we get something like this. So here it is the square root of x, y equal to square root of x. And if I take another function where it is cube root of x, then the graph would look something like this, cube root of x. So the domain of the square root function is 0, infinity. But the cube root function is defined for all real values of x. And now I can take further. So this one is clear, isn't it? A equals to this one where it takes up to square root of x, this one, and cube root of x. Now if I take y equals to x to the power 3 upon 2, then the graph would look something like this. If I take the opposite 2 upon 3, it would look something like this. So this is how the functions and their values and the different types of linear function, power functions, even and odd functions, they behave. And this is how the graphs look like. How do you calculate? How do you plot? What are the intervals? All these things I made clear in this video. So we will take a pause on today's video, and I would like to thank you immensely for watching this video. If you have liked, I will wait for your comments and reaction. Please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can write to me at this email ID, and you can subscribe and like to my other channel General Relativity Explained. You can follow me further on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with more videos on calculus as well as the other areas of physics and mathematics that you are following and that I am trying to teach you with more fun-loving and interesting videos. Thank you very much. See you in the next lesson. May the good Lord be with you.